Yeah, thank you very much for the invitation. It's great to join this meeting. So Q5D is a new company, or relatively new company, and it's coming at the kind of problem of printed electronics from a slightly different angle from some of the stuff that you've heard before. Although a lot of the underlying problems that we're trying to solve are pretty much identical, and we're coming at it from the wiring harness rather than the kind of small electronics side of things. And the reason for that is that we realized that wiring is pretty much still done by hand in processes that haven't changed all that much for 100 years. And often the layup of wiring is done on these kind of pin boards you see in the picture here. So although there is automation and they might use machines to cut wires and strip wires and sometimes to even do the terminations, at the plugs on the end, they'll still use some expensive people to do this wiring and then tie everything together. And so it is crying out for some kind of automation, and lots of people are trying to look at how to do that. It's a set of processes that is prone to error, and pretty much all product recalls in the world are at some point related to damaging on the wire, damage caused on the wire, either during the manufacturing process and errors in the manufacturing process, or because the insulation on those wires have become brittle or rub against another component, or and you get arc overs and fires and things like that. So automation and improving quality and improving the time of manufacture, the takt time for the manufacture, is where we came from. It's also much easier when you're looking at a kind of additive processes that we're looking at to try and target sectors of the economy which are done by hand. I mean, if you're trying to compete with bulk processes that that exist already, then you haven't really got a hope. But because this is a process that is relatively slow, we have a chance to compete both on cost, quality, and time. So the company Q5D is a spin out of two other companies. One of them is come from the additive world. It's called Cell UK and sells small desktop 3D printers under the Robox brand. And the other company is called MSolve. I'm sure many of you have heard of that because they are in the sort of printed electronics world. And they're experts in laser micromachining and machine processing and materials processing. And so we created a 5-axis machine. Use one on the right here, as you see the first one we built, a 5-axis machine that has an interchangeable head. And so you can swap out that head to put in any other kind of head that you like, to add wires or filaments, to do the terminations, to do printed electronics, to add insulation and surface mounting components. And so that you can take an existing component, mount that onto the machine, and then add things to it. Because there's no point in using FDM and additive manufacturing process. It's very slow. If you can take an existing component and add to it, it's a much more efficient method for manufacture, and improves your throughput completely. So it's multi-material 3D printing, aiming at, like I said, improving weight, cost, quality, and like I said, improving safety. Safety because if you're embedding the wires and the printed electronics into the component, you cannot get, particularly because we're dealing often with power electronics and power wiring, you can't get the wires getting close to each other because they're embedded. They cannot get close or fret next to each other. You don't get these arc over events and then fires. And also because you're sealing them in, the ingress of fluids to damage that wiring just cannot happen so easily. So you can create something that's inherently safer than existing wiring harness technologies. And one thing I'll talk about a little bit later, you are merging now the mechanical and electrical design of your components. So when you're doing your finite element analysis to study the strength of your component, if your wiring is embedded, you're also then doing a finite element analysis on the electrical subsystem as well, which is something that's very rarely done at the moment. And it means that you have to switch to a completely different way of designing products, but also you've got different ways of checking that the reliability of that product under stress and strain. So the first head that I wanted to talk about is the FDM head, and I think this has been mentioned that a few of the other, a lot of people are doing this kind of thing. It is obvious that you have to move to 5 axes, and the reason for that are manifold. One is that if you were trying to print this and I'm sure a lot of you are familiar with standard 2D layered additive manufacture, to create a structure of this type with its fine walls, you would have to print a whole bunch of support structures to accommodate the overhangs. In here, because you're printing onto an already solid structure, you don't need to do that. So your print speeds can be 5 to 10 times faster. But from the printed electronics point of view, you can arrange so that your smooth surfaces are the surfaces, there's always a rough stepped edge, and then there's it's still rough, but there's a relatively smoother surface onto which you can print your electronics. So it makes it easier if you're going to do printed electronics if you've got a 5-axis structure. Obviously, you can add to an existing component and a complex shaped component. The parts can be stronger because you can arrange your layers in the printed part to be aligned orthogonally to the stress axis of your component. So it has a whole bunch of important benefits going to these 5-axis structure, 5-axis machines. And one of the things, I know it's a printed electronics conference, but this is really quite important for us. We embed wires or add wires to structures. Either they're copper like this, or you can add an aerospace or an automotive qualified wire onto a material. And that's important because obviously electronics is great, and you can use printed electronics for that perfectly. But when you have any kind of level of power in the system, they don't work so well. And if you have very long tracks, and some of the things that we are working on, like the beds of and all the chassis of battery electric vehicles, then printed electronics are never going to cut it, because you really need to have wires for that kind of thing. Once you can embed wires, then obviously it's not just limited to that. Any kind of filament you can add. So we are projects on fiber optics, where you're adding fiber optic sensors or data transfer into materials, or you can add stiffening members. And again, that's really quite important. If you're want to do printed electronics onto a surface, they are very fragile structures. And adding a little carbon toe or a filament underneath that or around that to provide some stiffening, just so that under strain that piece of printed electronics doesn't break, can be very valuable indeed. We have kind of very standard, sorry about the picture, is what I found it as an example, but we have the standard kind of printed electronics, either paste extruder here, or we have from Pell, we have a jetting head. So we can print on complex structures and then build up structures with the FDM printer, and then add to it, and then overprint it. However, I have to say that this is not ideal for us, because the 3D print, the printed electronics is always just part of a larger construction or a larger build. And so you either have to build an oven into the machine, which we have been thinking about doing to cure the paste, or take the component out, put it in an oven, and then try and remount it back in exactly the same position afterwards. And that not only breaks up the manufacturing flow, it slows things down, and is a place where you can start to incorporate errors into the design, into the manufacture. We were going to a kind of a different process, which is one that was been developed by EMSOL, and it's been talked about at least by Neotech. They're doing something very similar, and that is to use lasers to sinter and cure a paste. It can be very efficient. In this particular case, you can sinter quite large areas very, very quickly. From our perspective, we are working with EMSOL to miniaturize the laser heads so that we can put this onto the robot arm, so that we can create large curved panels with printed electronics on it for various applications, but obviously some of which I can't always mention about. But what the benefit is on this particular case is that you get very, very good conductivities. Because you're sintering the copper or silver paste, you can get something that is close to about 1/3 of the conductivity of the pure metal. It's still slightly porous, so it never gets quite up to the full conductivity of the metal, but it's getting there. And you typically can get accuracies, depending on your print type, of about 10 microns. And as Neotech pointed out, if you use a laser to trim the structures afterwards, you can get down lower than that, down to 3 micron accuracies. We found, depending on the structures that we put it down on, it has extremely good adhesion, and because it's a very flexible process indeed. One of the other benefits from our perspective, because we're often going to quite low cost and large structures, is replacing the silver. The silver can be a prohibitive problem sometimes, and the ability to use copper pastes is very, very attractive. And as you know, copper is quite difficult with printed electronics to get good conductivities because of the oxide layers. But that's not really a problem when you're using the laser sintering processes. So this is a much more ideal printed electronics process for us. We haven't quite got it working on our machine yet. So MSOLV sell machines that work on flat surfaces, both polymer and glass, and we're in the process now with a large grant to adapt this to fit onto our robotic tools. As we said, the software is really very central to this, and the whole project, Q5D project, couldn't really occur if we didn't have methods to create or control the machine. But what's kind of interesting, so I'll jump really down to the CADCAM, which is kind of crucial. And we're working with Siemens NX, and what we realized is that quite a lot of the problems that we have in controlling these 5-axis additive machines have already really been solved by the CNC community. And they're taking things off and we're adding things too, so there's a plus and a minus problem. But if you start to think about things instead of in terms of layers, but in terms of lines filling space, which is what you do when you're machining off with a tool off a solid, and you reframe the problem along those lines, then it starts to become a tractable problem. Siemens NX have been very flexible with us, and at the moment we're able to create full digital twins of our machines so that we can pre-run the job to make sure there are no clashes, to get time and cost and other processes out prior to actually doing a run. Really important for us. It's also important, as I think has been said before, that we're now incorporating the electrical part of the system into the mechanical part. You're now designing those two things at the same time. In the past, the way that would have been done is you'd create your large structural part, and then you'd leave holes in that that you hope are large enough for your electrical subsystem to be pulled through or fitted in. And that's fine, but you often means you're breaking up that problem into different parts, and they're done by different engineers and often by different companies, often on different parts of the globe. And that can be a very, very slow process. But if you are incorporating them all together, and Siemens is doing that with a lot of their packages, starting to look at how to do that now, then once you've created that design, all you need to do is press the button. It does the toolpath calculation, it sends it down to the machine, and then you go away and come back the next morning and you have that part ready and waiting for you. You don't have to wait for some complex supply chain to provide all the different bits and pieces and then assemble it. It also means that you can use the more complicated computer-aided engineering like FEA to test the entire system to make sure that it's going to survive the vibration, it's going to survive the stresses and strains, both the electrical and the mechanical parts of your design. So that bit is off in the future, but I think it's a really exciting prospect, the ability to do that. I think I can finish with just one example that we can talk about. It's a grant we've just started now to work with Safran, the French aerospace company. Their first and business class seating, and again, it's interesting how similar some of these things are to some of what things that other people are doing. The composite panels they use, the lightweight composite panels they use to separate out the seating, has a lot of wiring on the back of it. It uses very heavy standoffs, it uses aerospace quality wiring, heavy terminations, and everything's made by hand. I mean, obviously a plane gets narrow as it gets towards the front of the aircraft, and so each seat is subtly different, and it's quite difficult to automate. But with an additive manufacturing process, that's not really so problematic. And so what we're doing with them is we're taking those composite panels, putting a layer of polymer onto that, embedding the wiring, and because it has to be aerospace qualified, we have to use aerospace qualified wires directly. Then terminating those, adding the terminations on the end, adding other components with the pick and place, surface mounted components. If we haven't actually started to, but we would love to start to try and we're trying to pitch at the moment to add capacitive controls onto those rather than normal switches. And then you can overprint and seal the entire system. And the reason why that's important is they're trying to move to biosecure cabins. It's obviously quite an important thing for the community at the moment. They're either doing that, they're either cleaning the place with UV, or they're cleaning it with some aggressive chemicals, and you don't want the wiring to be damaged. And also you don't want any touch points. So the idea of using capacitive and other slightly less touch controls is gaining quite a lot of traction in the airline industry. So I'm gonna stop there and hand back. Thank you for your attention.